Light travels at 300,000 kilometers per second. Fastest thing in the universe. Nothing beats it. But what if you chase it? Run after a beam of light? Get closer to light speed yourself. Does the light slow down from your view? If you're running at 10 kilometers per second, does the light only pull away at 299,990 kilometers per second? What if you reach 299,999 kilometers per second? Does the light barely crawl ahead of you at 1 kilometer per second? Light speed is relative to the observer. Sounds right. That's what everyone says. But it's backwards. The answer breaks common sense completely. It forces time itself to bend. The light doesn't slow down at all, not even slightly, which means something else has to. Your intuition says speed should subtract. If you're running at 10 kilometers per second toward a person throwing a ball at 20 kilometers per second, the ball approaches you at only 10 kilometers per second. Simple addition and subtraction. So if you chase a beam of light while moving at close to light speed yourself, the light should slow down from your perspective. Makes perfect sense. That's what everyone thought, including me at first. But then, in 1887, two physicists named Michelson and Morley measured the speed of light in different directions. The Earth orbits the Sun at about 30 kilometers per second. So at different times of year, we're moving in different directions through space. They expected to measure light traveling faster in some directions, slower in others, like measuring wind speed from a moving car. You'd expect the wind to seem faster when you're driving into it, slower when it's at your back. The result? Light speed came out identical. Every direction, every season. Not approximately the same, exactly the same, down to the precision of their instruments. Physicists tried explaining it away. Maybe the Earth drags some invisible medium along with it. Maybe measuring rods contract just enough to hide the difference. But the measurements kept coming back the same. Light doesn't care how you're moving, which forced a question nobody wanted to ask. What if light doesn't slow down? Ever? Imagine you're on a train moving at 100,000 kilometers per second. You shine a flashlight forward. From the ground, someone measures that light beam traveling at 300,000 kilometers per second. From your perspective on the train, common sense says the light should crawl away from you at only 200,000 kilometers per second. Right? Wrong. From your perspective on the train, the light still travels at 300,000 kilometers per second. Same speed. Exactly. Your friend on the ground measures it at 300,000 kilometers per second. You on the train measure it at 300,000 kilometers per second. How is that possible? Both of you are moving relative to each other. The light beam is the same beam, but you both measure it at the same speed? Here's the thing. If light speed stays constant, something else has to give. Work backwards from the requirement. You and the ground observer must both measure light at the same speed, but you're moving relative to each other at 100,000 kilometers per second. Speed equals distance divided by time. If the speed stays the same, but you're moving, either the distance changes or the time changes. Actually both. But start with time. Picture a clock made from light. A light pulse bounces between two mirrors. Tick-tock, tick-tock. From your perspective, moving with the clock, the light goes straight up and down. Simple. From the ground observer's perspective, though, you're moving. So while the light bounces up and down, the whole clock is also moving sideways. The light traces a diagonal zigzag path. That's a longer path for the light to travel. Longer path means it takes more time for one tick. But light speed must be the same for both observers. That's the rule we just established. The only way that works, your clock runs slower from the ground observer's view, not malfunction. Time itself runs slower, not seems to run slower. Actually runs slower. Real, measurable difference. Let me prove it to you. GPS satellites are flying overhead right now. They orbit at about 20,000 kilometers altitude, moving at 14,000 kilometers per second relative to the Earth's surface. Time dilation predicts their clocks should run slow by about 7 microseconds per day compared to clocks on the ground. Doesn't sound like much, but GPS works by timing light signals to nanosecond precision. Light travels about 30 centimeters in 1 nanosecond, so 7 microseconds of error means your position is off by about 2 kilometers. The engineers who built GPS had to program the satellites to account for time dilation. Otherwise, the system becomes useless within hours. This isn't theoretical speculation. It's an engineering requirement. We've also sent atomic clocks on airplanes. In 1971, Heffel and Keating flew atomic clocks around the world and compared them to clocks that stayed on the ground. They measured differences of a few hundred nanoseconds, exactly as predicted by the equations. Or take muons. These particles are created high in the atmosphere by cosmic rays. A muon lives only about 2 microseconds before it decays. At the speed they're traveling, they shouldn't make it to the ground before decaying. But they do reach the surface. Why? Because from our perspective, they're moving near light speed. Time dilates. They live longer. From the muon's own perspective, though, its clock ticks normally, but the atmosphere is contracted, thinner, so it doesn't have as far to travel. Both perspectives give the same result. The muon reaches the ground, and that's just moving through space. What about light itself? Get in a spaceship. Accelerate to 99% of light speed. Now shine a flashlight forward. You measure the light beam, still moving at 300,000 kilometers per second, pulling away from you at full speed. How? Your time has slowed down from Earth's perspective. Your rulers have contracted from Earth's perspective, but from your own perspective, everything seems normal. Your clock ticks at what feels like a normal rate to you. Your ruler measures lengths that seem normal to you, and light still moves at 300,000 kilometers per second relative to you. Meanwhile, an observer on Earth sees your clock running super slow. They see your spaceship squashed in the direction of motion, length contraction. When they calculate the speed of light using your slowed time and your contracted distances, they get 300,000 kilometers per second. The conspiracy is perfect, not conspiracy. Geometric necessity. Go faster. 99.9% of light speed. Time slows more, length contracts more. Light still escapes at full speed from your perspective. 99.99%? Same thing. As you approach light speed, time dilation approaches infinity. Length contraction approaches totality. You can never catch up. Which brings us to the impossible. Question: what if you actually reach light speed? To reach light speed, time would have to stop completely. Length would contract to zero. It's physically impossible for anything with mass. Why? It requires infinite energy. As you accelerate faster, you get heavier. Your mass increases with speed. Takes more and more energy to accelerate further. Approaching light speed, your mass approaches infinity. You'd need infinite energy to reach it. Light itself has no mass. That's why it can travel at light speed. Photons don't experience time. From a photon's perspective, if it had one, emission and absorption happen instantaneously. The journey from a distant star to your eye might take 1,000 years from our perspective. From the photon's perspective, it's zero time. No time passes at all. So here's what changed in my thinking. I was 16 years old, thinking about light and Maxwell's equations. I imagined riding alongside a beam of light, matching its speed exactly. What would I see? The light should appear frozen, a stationary electromagnetic wave, just hanging there in space. But Maxwell's equations, which describe how light works, don't allow stationary electromagnetic waves. They always propagate. They always move at a specific speed through space. That's built into the mathematics. Contradiction. I spent 10 years resolving that contradiction. The answer: you can't ride alongside a light beam. It's impossible. Not just technologically impossible, fundamentally impossible. Light speed is the same for all observers because it's built into the structure of space-time itself. It's not just a property of light, it's a property of reality. More precisely, it's the speed of causality, the speed at which cause can affect effect. Light happens to travel at that speed because photons have no mass. But that speed, that cosmic speed limit, exists independent of light. Space and time aren't separate things that just exist independently. They're woven together into a four-dimensional fabric. Your motion through space trades off with your motion through time. Sit perfectly still in space. You move through time at the maximum rate. Move through space. You move through time slower. Light moves through space at the maximum possible rate, so it doesn't move through time at all. And this is where it gets stranger. If time is relative, then now is relative. Events that seem simultaneous to you don't seem simultaneous to someone moving at a different velocity. Example: two lightning bolts strike a train track. An observer, standing at the exact midpoint between them, sees the light from both strikes arrive at the same instant. To that observer, the strikes were simultaneous. But an observer on a train moving along the tracks sees one strike before the other. Both observers are correct. There's no universal now, spanning the entire universe. Well, there's a now for you, your present moment. But it's not the same as now for someone else, moving relative to you. Your present moment is tilted differently through space-time than someone else's, which means parts of what you call future are already in someone else's past if they're moving fast enough in the right direction, and vice versa. Remember chasing the light beam? As you speed up, your now tilts through space-time. Events that seemed in your future tilt into your present. Events in your present tilt into your past. But the light always escapes at the same speed because light defines the tilt. Light speed is the cosmic speed limit because it's the conversion rate between space and time. Moving faster through space means moving slower through time. The exchange rate is exactly the speed of light. That's why nothing can exceed it. You'd have to move backwards through time. Which raises the question I couldn't answer then. What is light, really? It's not just electromagnetic radiation. It's the messenger of causality. The speed at which reality updates itself. When I change something here, information about that change propagates outward at light speed. It can't go faster. That would mean effect before cause. The universe uses light speed to keep cause and effect in the proper order. But why that speed? Why 300,000 kilometers per second and not some other number? You asked what happens if you chase light. The answer? You can't catch it, no matter how fast you go. Not because the light speeds up to escape you, because the faster you chase it, the slower your time runs, the more your space contracts. The conspiracy maintains itself perfectly at every speed. Light speed stays constant because it's the structure of space-time itself. Everything else, time, distance, mass, simultaneity, bends around that requirement. Imagine, I spent 10 years working on this problem because frozen light waves seemed wrong. They violated Maxwell's equations. The answer I found? Nothing freezes light. Instead, everything else, time, space, reality itself, warps to protect light speed. The universe rearranges itself to maintain that one constant. Why is space-time curved near massive objects? That's gravity. Different story, but it comes from the same geometric necessity, the same requirement that space and time must form a consistent four-dimensional structure. I'll leave you to imagine the rest.